Hello and welcome to this clip on rates and orders. We'll look at how rate of reaction can be quantified using something called the rate equation, which contains the rate constant. How we use reactant orders to quantitatively determine to what extent the concentration of a certain reactant affects the overall rate of reaction, and how these orders can be proven experimentally using the initial rates method. We'll then go on to look at how we can use graphical methods, including the determination of half-lives of a reaction, to determine reaction order. And we'll go on to look at the effects of the rate determining step in a multi-stage reaction mechanism. For all of this to make sense, it's assumed that you've already covered what factors affect reaction rate from your first year of A-level chemistry. If you haven't had a look at that for a while, you might want to go back and look at your notes from your first year before proceeding. But if so, if you're confident on those areas, then we can go ahead. So we have two standard units we use to measure the two things that are needed for determination of the rate of reaction. We need to determine concentration and we need to determine time. So if we take the basic premise that the rate of reaction is equal to the change in concentration divided by time, and we convert that into units, what we can then do is inverse the seconds and call the unit moles per decimeter to the -3, second to the -1. So this is now the standard unit for rate of reaction. And this is what we use when we do rate of reaction calculations. So we can often work this out graphically by plotting the concentration against time. Time on the x-axis, concentration on the y-axis. So the gradient of the curve at any given point will be taken by the tangent and be in moles per decimeter to the -3, second to the -1. If the concentration of a reactant is changed, this often leads to a change in the reaction rate. But the amount of change that happens might not be the same for every reactant. So the concentration of some reactants might have more of an overall bearing on the rate of reaction than other reactants. So we mathematically quantify this variation of effect on overall rate between one reactant and another using something called the rate equation. You may recall from your work on KC that the concentration of something is signified by putting it in square brackets. So this is the concentration of reactants A and B that we've got here. So K represents the rate constant, and M and N are the powers to which the concentrations of the reactants are raised. This is called the order of reaction with respect to that reactant. And obviously this equation is going to require a little bit of explanation, so I'm going to talk about that in a second. So we can say that rate is proportional to concentration, and the power to which the concentration is raised in the rate equation is called the order. So for this particular example, the overall reaction order would be the sum of all the orders. So in this case, M plus N. So that we're able to work out the rate of reaction using a linear mathematical expression that can be put into a calculator, we use the rate constant to deal with the proportionality in the relationship. So let's have a quick look at the effect on rate of reaction of changing the concentration of reactants that have different orders. If you have a first order with respect to a certain reactant, if the concentration is doubled, the rate also doubles. If you have second order with respect to a reactant, the rate quadruples, increases by a power of 4, or sorry, by a factor of 4, if the concentration is doubled. And if the concentration is doubled with the order being third order with respect to a particular reactant, the rate increases by 8. So why does this happen? So if we now apply the idea of the order with respect to A being 1, if you double the concentration of A, you double the rate. If, however, the order of A is now, order with respect to A rather, is now 2, or second order, if we increase the concentration of A by 2 this time, the rate increases by 2 to the power of 2. So the order is in red, as you can see at the bottom of the screen. So 2 to the power of 2 means an increase in the rate times 4. So if we now change the rate equation so that K times A, concentration of A, is such that A is to the power of 3, in other words, it's third order with respect to A, if we again multiply A by 2, the concentration of A by 2, this time the rate will increase by 2 to the power of 3, the power of that order. Therefore, it will increase by a factor of 8. So we also have zero order. What happens there is that there's no effect on the rate when the concentration of a reactant is altered. So what we want to look at is the effect on the unit of K, on the rate constant. So that's how you'd write out the rate equation with respect to a certain reactant. So for the moment we're assuming only one reactant in the rate equation for now. We'll look at what might happen if there's multiple reactants in the rate equation on the unit of K in a minute. So if you look at raising anything to the power of 0, it gives you itself. So it gives you K times the concentration of A to the power of 0 gives you K. Because anything to the power of 0 is 1. So just to recap on that, A in concentration of to the power of 0 is 1. 1 times K is K, hence why the rate equals K for a zero order reaction. For the next one we have to divide rate over the concentration of A to the power of 1, which gives us those units, which can be partially cancelled to give us second to the power of minus 1. For an overall order of 2 is decimeter cubed mole to the minus 1 second to the minus 1. And for third order reaction overall, you get decimeter to the power of 6 mole to the minus 2 second to the minus 1. And so on and so forth. So just to remind you, the overall order is always the sum of the individual orders of the reactants. So if we take a moment to have a look at that, in the rate equations on the right, if you add up the individual orders, the powers to which the concentration are raised, in each case it should equal the overall order on the left hand side. So with the first one, it's no surprise, K equals rate divided by the concentration of B. Remembering that the concentration of A raised to the power of 0 is like anything raised to the power of 0, in other words it's equal to 1. And for overall order of 2 it's the same as the previous scenario when you just had one reactant in the rate constant. So it's the overall order that's determining this, isn't it? So let's try it for the final one. And that gives us, for third order overall, decimeter to the power of 6 mole to the power of minus 2 second to the power of minus 1, just like before. So the gradient of our tangent, which is the change in y divided by the change in x, will provide the initial rate of reaction in moles per decimeter to the minus 3 second to the minus 1. So this can be changed in successive experiments by adjusting the initial concentrations of each reactant, as you can see. So if you look at experiments 1 and 2, the concentration of A is doubled from 0.5 mole per decimeter to the minus 3 to 1.0 mole per decimeter to the minus 3. So the reaction has to be second order with respect to A because the initial rate has increased by 4. So in other words, the factor by which the concentration has been multiplied, which is 2, has been raised by the power of 2. So 2 to the power of 2 gives you 4. So 4 is the factor to which the rate has been multiplied. So that power is the order. So now let's look at determination of the order with respect to B. So now what we do is we find another pair of experiments where A remains unchanged. So in this case it would be 2 and 3. Here B is doubled, the concentration of B is doubled, but the initial rate remains the same. So therefore the order of the reaction with respect to B is 0. So this data shows that B does not affect reaction rate. So therefore the rate equation for this particular reaction would be rate equals K times the concentration of A. B would not be in the rate equation. Oh sorry, K times the concentration of A squared. Do beg your pardon, because we did say it was second order, didn't we? So it's important to point out that just because there happens to be 2 moles of A and it's second order, those two aren't linked to each other. The rate equation orders do not necessarily match the mole ratios in the equation. You do have to actually use initial rates data to work this out. So by repeating the experiment several times and slightly adjusting the concentrations, that's the only way that we can prove reaction orders, and we have to graph the results like we've shown you on the left hand side of the screen every time to get the tangent, to get the rate of reaction, to get our final column, fourth column in the table, and then we can have the data to prove what the reaction orders are. We don't just get it from the mole ratios. So there's several techniques that we have available to us for monitoring rate continuously throughout a reaction. We can use colorimetry, which allows us to measure the fading or deepening of a colour of a reaction mixture by passing light through it and measuring how much absorbance of light is happening once the light has passed through the solution. And you'd plot time against absorbance in this case. So there's several different ways you can do it, but each method will involve plotting time against a change in mass or an absorbance or change in gas volume, for example. So all these are perfectly legitimate ways of measuring the rate continuously throughout a reaction. But to obtain the rate of reaction, you must take a tangent and measure its gradient. If you were to change the concentrations and replot several times, this would again give you initial rates data similar to the data we had on the previous screen. Some further work we can do with a colorimeter involves plotting the concentration, different concentrations of the coloured chemical against absorbance. What this gives us is a calibration curve, it may even be in the form of a straight line. So if you now plot the time against absorbance whilst your reaction is going on, so you're shining the light through the colorimeter, through your reaction and into the colorimeter whilst the reaction is going on, over time you'll get a series of absorbance readings for which you can do a curve of best fit or a line of best fit. So if you take each absorbance that you've plotted and use the calibration curve that you've worked out already to work out a concentration for each absorbance. So the thing about a concentration time graph is its shape can be used to determine the reaction order. So this is an alternative way of working out reaction order using graphical methods. So you can use rate versus time or concentration versus time to work out the reaction order from the shape of the graph. So the calibration curve that we had in the previous screen allowed us to convert absorbance into concentration and therefore have a concentration time graph to compare to these shapes. So we can also plot a concentration time graph and get the half-life. The half-life is the time taken for the concentration to drop to 1/2 of what it was before. If the half-life remains constant, the reaction is first order with respect to that reactant. We can also calculate the rate constant K from the half-life by taking the natural log of 2 and dividing it by the half-life. So in this case, it's the natural log of 2 divided by 55 approximately, and that gives you 0.0126. Now we don't know what the order with respect to any other reactants are, so therefore we don't know what the overall order of the reaction is. Once we know the overall order of the reaction, then we can assign a unit to K, but at least we know what the value of K is at this particular point. But let's assume this was a first order reaction overall. In that case, we'd be able to assign a unit of seconds to the -1. So this method is actually more accurate than using tangents, as the exact gradient of the tangent to be drawn can be quite hard to judge sometimes. So this is a mathematical way of getting around that problem. Finally, we can use rate concentration graphs. These will also have certain shapes for each order of reaction. So So first of all, the zero order reaction will just give you a horizontal line as you'd expect. So as we've looked at before, zero order means there's no change in the rate with concentration. The first order graph will give you a straight line of fixed gradient. And the second order will give you a curve. So these need to be remembered so that you can actually apply them to examples given in exam questions. So many reactions that we work with don't happen all at once. We just see the end product, but the actual reaction happens in several stages, because to get everything to collide with the sufficient activation energy and in the right way is actually quite difficult in many cases. So if we were to take a typical example like, I don't know, the hydrolysis of a haloalkane like this, that would be the overall reaction that you'd expect to happen. That's all very well, but does that actually happen in reality? So let's have a look at this in close proximity. Tertiary haloalkanes like this one have a slightly different way of reacting during nucleophilic substitution. Because of the relative crowding of the delta positive carbon with those bulky CH3 groups, the first step is the actual breaking, fission, heterolytic fission of the C-Br bond. And this is a slow process. The second step is much faster. Now the OH- nucleophile attacks the carbocation at the positive carbon atom. This is the fast step. So the slower step out of these two is called the rate determining step. Only its reactants will appear in the rate equation. As you can see, no sign of OH-, even though it's an overall reactant. So the thing to remember is the mole ratios of the reactants in the rate determining step will be the same as their orders in the rate equation. It's a useful one to bear in mind for exam questions when we start to have a look at them in a minute. So let's now look at how you might be expected to do this in an exam. Imagine I hadn't just explained the two-step mechanism with curly arrows and lone pairs and dipoles. You'd be expected to come up with a possible mechanism just using the information below. So I'm not talking about the curly arrows or lone pairs. You wouldn't be expected to come up with that level of detail. What they're looking for is can you work out from the overall equation and the rate equation what the steps in the reaction are. Well, we can start by writing this out. Let me try and explain what each one means. If you look at the rate equation, you know that there's only one species in the rate determining step. So that's the slowest step. So step 1 can be the rate determining step. So looking at the rate equation, we know that there's one mole, that it's first order, I beg your pardon, with respect to the tertiary haloalkane. So if it's first order in the rate determining step, then that means there must be one mole of it in the equation for the rate determining step. There's only one reactant in the rate determining step, so there's only one reactant in step 1. So because I've got two products in the overall equation, if it's a two-step process, then each product is made in a separate step. So you can see that the alcohol is made in the second step, so the bromide ion can be made in the first. So now what we have to do is work out how to make the alcohol using the OH-. It's obvious, you'd have the carbocation. So if you now cancel any species that are present in both steps, and you can then combine what's left to create the overall equation, as you can see at the top of the page. So I've now annotated what's been used and what's been made in each step in the main equation, so you can relate that to the two steps further down the screen. So let's now try some examples. Now it says for each reactant, deduce the order of reaction and show your reasoning. What I'm going to do is I'm going to make the page a little bit smaller so we can do any necessary workings at the side. So let's start with the H+. all we've got to do is find a pair of experiments where it's changed, but everything else stays the same. So you can see that the concentration of H plus is doubled in going from experiment 1 to experiment 3. The concentrations of BrO3 minus and Br minus remain the same. So it's first order with respect to BrO3, because if you look at experiments 1 and 2, H plus and Br minus remain the same, but the BrO3 minus concentration doubles and the rate doubles, so that means it's first order. So now I'm looking at experiment 3 and 4 because they're the only experiment pair where the bromide ion concentration changes. So there are no reactants that remain the same concentration here, so we're going to have to take a slightly different mathematical approach. We know that H plus is second order, so going from experiment 3 to experiment 4, the H plus concentration halves, so it's multiplied by 0.5. You raise that to the power of 2 because it's second order. That gives you 0.25, so you divide the rate by 4, which is the same as multiplying it by 0.25. So the rate goes from 6.72 down to 1.68 times 10 to the minus 5. That's just because of the H plus. So the concentration of bromate, BrO3 minus, is increased by 3. We know it's first order, so you raise that to the power of 1, so that keeps that as 3. So you take the 1.68 times 10 to the minus 5 you had before from the effect of H plus, multiply that by 3, and that gives you 5.04 times 10 to the power of minus 5. So what you've now got to do is think the final rate is 1.01 times 10 to the minus 4. What had to happen to 5.04 times 10 to the minus 5 to get to that final rate? It had to be multiplied by 2. So it must be first order with respect to bromide, Br minus. So the final thing they want us to do is to deduce the rate equation for the reaction. So all you do is you take in the concentrations of each of the reactants, raising to the power of the order where necessary, and that gives you rate equals K times the concentration of H plus squared times the concentration of bromate times the concentration of bromide. Okay, so let's turn the page over and have a look at the next part of the question. So you start by writing out the rate equation, because they want you to calculate the rate constant, and then you rearrange the rate equation so that K is the subject. So now what you do is you take the equivalent data for H plus concentration, BrO3 minus concentration, and Br minus concentration from any one experiment. So I've taken experiment 1's data and popped it in. It gives me 0.015, and I've cancelled appropriately, putting the units in at the top and the bottom of the expression. So the units this time will be decimeter to the power of 9, mole to the minus 3, second to the minus 1. So the next part of the question asks us to suggest how the initial rate of bromine formation would be calculated from a concentration time graph. So you take a tangent at t equals 0 and calculate its gradient to get the initial rate of bromine formation. So let's move the page down to see what else they want. And then finally it asks us to say what evidence is there that this reaction proceeds by more than one step. So to answer this question, what we've got to do is compare the rate equation with the actual balanced equation, and you'll see that the mole ratios in the balanced equation are not the same as the orders in the rate equation. So we pop that down as our reasoning. Okay, so let's have a look at the mark scheme to see how we did. So we compared experiment 1 and experiment 3. We got order at 2 for H plus, and we talked about the rate increase by 4. We did the same for BrO3 minus, and for Br minus we had the 2 increases that we had to deal with. So that gives us the rate of rate equation K times H plus squared times BrO3 minus times Br. So the next stage was to rearrange the rate equation and put in the numbers, which we did, which gave us 0.015 and the correct units. So we got 4 for that one. And we correctly said that there was a gradient at t equals 0. And then for the final part, bring the mark scheme down slightly, the overall equation has different number of moles to the orders in the rate equation. So that gives us 13 marks in total. So if you've got any queries on this, do bring them into your lessons, have a chat to your teacher, maybe bring it into one of our subject extensions. But either way, thanks for your time once more, and see you soon.